Chapter 17, Global Change. Alternative climates and alternative choices, ozone and the stratosphere, CFCs and ozone depletion, greenhouse gases and global change, modeling global climate change, a warmer world, and what can be done. Ozone hole over Antarctica and global temperature record. Are these two things related? It is a common misconception that ozone depletion causes global warming. However, both are global scale issues related to the atmospheric composition, ozone in the stratosphere and CO2, and some other greenhouse gases in the troposphere. The ozone layer is Earth's own sunblock system that stops 97 to 99% of the harmful incoming ultraviolet rays from reaching the planet's surface. There are three types of ultraviolet radiation: UVA, UVB, and UVC. UVC, the shortest wavelength and the most dangerous, is filtered out by the atmosphere. UVA and UVB cause skin cancer and wrinkles after repeated long-term exposure. UV rays can penetrate your clothing. An SPF 15 lotion blocks out about 92% of the UV that reaches Earth's surface. Here, ultraviolet radiation causes oxygen molecules to break into two atoms. An individual atom combines with an oxygen molecule to form an ozone molecule. Then, the UV radiation breaks the ozone molecule down to an oxygen molecule and an oxygen atom. The formation of ozone is cyclical. The UV radiation breaks an O2 molecule into two separate oxygen atoms. An individual oxygen atom combines with a whole O2 molecule to form an ozone molecule. UVB strikes an ozone molecule and breaks it back down into an O2 molecule and a single oxygen atom. This oxygen atom is then free to combine with another O2 and make more ozone. No long-term change in the concentration of ozone occurs. The three steps of natural ozone production and destruction in the stratosphere. UV radiation is converted from light to heat by the destruction of oxygen molecules and ozone molecules. The temperature rises with increasing altitude in the stratosphere. Global variations in ozone concentrations, March 2016. Ozone concentrations increase with latitude. The concentrations are greater in the Northern Hemisphere during the Northern Hemisphere's spring, and greatest in the Southern Hemisphere during the Northern Hemisphere fall. The following graph represents the variation in ozone concentrations over 4 cities: Darwin, Australia at 12 degrees south, Melbourne, Australia at 37 degrees south, San Francisco, USA at 37 degrees north, London in the United Kingdom at 55 degrees north. Explain which city goes with each of the 4 plots. What are chlorofluorocarbons, or CFCs? They are volatile organic compounds used as aerosol propellants and refrigerants. They are inert, or non-reactive gases that remain in the atmosphere for up to 200 years. They can be broken down by photolysis, UV radiation, which frees the chlorine atoms from the CFCs. Chlorine atoms react with ozone, destroying an ozone molecule and creating chlorine monoxide and oxygen. And there is the chemical formula for that. Chlorine monoxide reacts with oxygen atoms, freeing up another chlorine atom available for breaking down ozone. 80% of chlorine in the stratosphere comes from chlorofluorocarbons. In 1978, per the Montreal Protocol, the U.S. banned aerosol sprays containing CFCs and phased out their production. However, other countries, even to this day, still use CFCs. The ozone hole is not an actual hole. It's just an area of reduced ozone. Why is ozone depletion concentrated over Antarctica? The unique weather patterns over Antarctica, the polar vortex. The temperatures are 112 degrees Fahrenheit below zero, June through August, which leads to the formation of polar stratospheric clouds, water and nitric acid. The ice particles in these clouds provide surfaces on which chemical reactions can occur, including the release of chlorine by chlorine-bearing compounds. In the spring, which is September through November in the Southern Hemisphere, the temperature rises. Processes that produce ozone outpace the destruction, and ozone begins to increase. There's no polar stratospheric clouds elsewhere. It means less ozone loss elsewhere. Ozone formation and destruction are temperature-dependent phenomena. Here's a graph showing the chlorine concentrations in Earth's atmosphere. What do these two graphs tell you? What trends do you notice? What does this imply for our ozone layer's future? The changes in CFC concentrations in the atmosphere. Here are the years, and along here, parts per thousand. The CFC concentrations. Infrared radiation emitted from Earth's surface is absorbed by water, CO2, and other trace gases in the troposphere, creating a situation known as the greenhouse effect. We like it because it keeps the average surface temperature of Earth 59 degrees Fahrenheit as opposed to 0 degrees Fahrenheit. We can have too much of a good thing. Venus has runaway greenhouse effect with average surface temperature of 885 degrees Fahrenheit. The 20th century was the warmest in the last millennium, and the 10 warmest years in the last 1,000 have occurred since 1998. Key points. The greenhouse gases help warm the planet. We do need it. Global concentrations of greenhouse gases have increased. The average global temperatures have increased by more than 1.53 degrees Celsius or 2.8 degrees Fahrenheit over the last 100 years. The population growth will contribute to increased concentrations of greenhouse gases in the future. The carbon cycle. The biosphere carbon reservoir, the plants on land and in the ocean represent a net carbon sink. The U.S. forests are absorbing more CO2 today compared to 100 years ago due to the regrowth of forest on previously logged lands. The trees. Carbon is absorbed by photosynthesis and released when trees decay. Carbon can be stored for decades or centuries. The soil. Carbon can be stored for up to thousands of years. There's about twice as much carbon in the soil as there is in the atmosphere. Fields. Deforestation. Carbon is released as vegetation is burned. Natural vegetation, for example rainforests, may be replaced with agricultural plants that absorb less carbon dioxide. Animals. Carbon is released by respiration, by breathing out. The anthropogenic CO2 emissions. Land use changes, fossil fuels. The cities. Carbon sources from consumption of fossil fuels in industrial processes, electricity generation, and transportation. The atmosphere carbon reservoir. Approximately half of the anthropogenic carbon emissions contribute to an increase in the concentration of atmospheric carbon dioxide. There's an annual flux of carbon between the hydrosphere and the atmosphere. Hydrosphere carbon reservoir. Most carbon remains in deep ocean water for hundreds of years until brought to the surface by upwelling currents in the oceanic conveyor belt. Carbon is in constant flux between all of Earth's components. The atmosphere is both a sink and a source of carbon compounds and carbon-based gases. The carbon enters atmosphere via respiration, animals exhaling CO2, the burning of forests, the decay of dead organisms, the burning of fossil fuels, natural volcanic activity, and the release of dissolved gases from the ocean. The atmosphere is both a sink and a source of carbon compounds and carbon-based gases. Carbon leaves the atmosphere via photosynthesis, rock formation, absorption by the ocean, other biological processes. Overall, more carbon enters than exits the atmosphere by about 3.4 billion tons per year. Variations in carbon dioxide concentrations are shown in this graph. Do you notice any trends? How do you explain each one? Where on Earth would you expect to see the most pronounced seasonal CO2 variations? Why? There's a sawtooth pattern. That's because it's seasonal. The fluctuations in the CO2 are due to plant activity. The overall increasing trend, or the buildup of CO2 in the atmosphere, is mainly due to human activities. The hydrosphere. Oceans act as a carbon sink by absorbing more gas than they release. The oceans retain an additional 2 billion tons of carbon per year. The amount of CO2 oceans can absorb increases with decreasing temperature and increasing wind speed. The wave action helps by creating bubbles that transfer the gas from the air to the water. The CO2 falls in streams as acid rain, and it enters the oceans via runoff. Carbon is carried to deep oceans in cold sinking currents and remains there for more than 1,000 years. It's a long-term reservoir. CO2 is released back to the atmosphere as warm water rises, like bubbles out of a warm can of soda. The biosphere. It interacts with all other parts of the Earth's system through the carbon cycle. Plants extract CO2 from the atmosphere by photosynthesis. Animals eat plants, thereby consuming carbon. Carbon is returned to the atmosphere when organisms die. Carbon can be held for millions of years if organic remains are buried and converted to fossil fuel deposits like coal, oil, and natural gas. Carbon is retained in some marine animals as part of their shells or skeletons. Dead marine organisms sink, getting buried, locked in sedimentary rocks, locking away their carbon. The geosphere. The largest sinks for carbon on the planet are rocks and minerals of the solid earth. Most is present as an element of calcium carbonate or limestone. When limestone undergoes chemical weathering, it releases CO2 to the atmosphere. Chemical weathering is caused by acid rain, which takes CO2 out of the atmosphere. Some carbon is stored in fossil fuel deposits formed from decayed organic material. Overall, CO2 in the atmosphere remained constant at 280 ppm on a global scale for several centuries prior to the Industrial Revolution. Anthropogenic emissions of greenhouse gases such as CO2 rapidly increased in recent decades. Most anthropogenic emissions come from consumption of fossil fuels and deforestation. About half of what we produce is taken back into carbon sinks in the biosphere and oceans, and the rest is just left in the atmosphere. The anthropogenic or human-produced and atmospheric carbon dioxide compared. The human production of carbon dioxide in relatively large concentrations began in the 1800s, at the same time as the concentration of carbon dioxide in the atmosphere began to increase. The volume of anthropogenic carbon dioxide can be readily calculated on the basis of the volume of fossil fuels consumed. The principal U.S. greenhouse gases by source type. Water vapor accounts for most of the natural greenhouse effect, but human-produced water vapor is not a factor in global warming, so it's not represented here. The principal U.S. greenhouse gases by sector. While energy is the largest sector, multiple stakeholders share nearly equal responsibility for emissions, and they all use energy. These pie charts show the global emissions of anthropogenic greenhouse gases. CH is methane, N2O is nitrous oxide, F gases are the fluorinated gases. The first pie graph shows the share of emissions by greenhouse gas, and the second pie graph shows the share of greenhouse gases by sector. The annual carbon emissions for the continuous United States. This map shows the annual emissions in 2002. The large red patches are the urban centers, and the small red dots represent individual point sources, for example, power stations or factories, and the linear patterns are major highways. How would you expect this figure to change over the next 50 years? The global warming potential of a gas depends on its ability to hold heat and how long it stays in the atmosphere. Carbon dioxide has a longer lifetime, decades to hundreds of years, but it absorbs less heat. Methane absorbs a lot of heat, but it remains in the atmosphere for much shorter time periods. The GWP of methane is 21 times greater than that of carbon dioxide. Where are the most greenhouse gases concentrated? Initially, they are concentrated where there is more human activity. 4 countries produce more than 1/2 of global emissions: China, the US, India, and Russia. Atmospheric circulation patterns thoroughly mix the gases and distribute them throughout the troposphere. Greenhouse gas concentrations are remarkably uniform worldwide. This shows the distribution of global carbon emissions. Data for the 20 nations with the greatest emissions in 2014 are listed here. Emissions of carbon dioxide vary hugely between places due to the differences in lifestyles and ways of producing energy. For example, compare the emissions from different continents. These data will change annually. Check online to see the recent statistics and discover the most significant changes. How do you think this map will change and look 50 years from now? Forcings and feedbacks. Example, audio feedback. A speaker hooked up to a microphone to amplify sound. The microphone picks up sound coming from the speaker, further amplifying it. The sound is a forcing mechanism. The result is a high-pitched squeal or feedback. Forcings and feedbacks are important parts of climate change. Sunlight is scattered, absorbed, and/or reflected by Earth. More reflected is more cooling. More absorbed is more warming. Earth's radiation balance: 1/3 is reflected. The rest is absorbed by the atmosphere and land and water of Earth's surface. The infrared is absorbed and re-emitted toward Earth's surface by greenhouse gases. Approximately 1/3 of the incoming solar radiation is reflected, and it ends up back in space. The rest is absorbed by the atmosphere. The infrared from the heated surface is trapped by greenhouse gases in the atmosphere, adding more warmth to our atmosphere. An increase in the greenhouse gases adds 2 to 3 watts per square meter more warming to the atmosphere. Climate forcing: any phenomenon that causes a change in the global solar radiation balance. Positive forcings lead to global warming. Negative forces lead to global cooling. Examples: positive forcings: more solar energy reaches Earth's surface. More energy is absorbed by the addition of greenhouse gases. Negative forcings: volcanic ash reflects light back into space. Increased ice cover causes more reflection off Earth's surface. It's measured as radiative forcings. Modeling global climate change. Climate forcings. Relative forcings, or RFs, are expressed in watts per square meter. The warming effect of greenhouse gases was partially offset by forcings due to human activities, such as industrial pollutants in the form of reflective aerosols. Some forcing agents, for example clouds, have considerable uncertainty as to their degree of forcing. The net effect of forcing is to warm the planet by 1.6 watts per square meter. Aerosols are tiny reflective particles. It makes them a negative forcing mechanism. Some black particles absorb solar radiation and can cause warming. Warming or cooling caused by forcings leads to other climatic feedbacks that can exaggerate or reduce temperature changes. Examples: warmer climate equals more evaporation, equals increased greenhouse feedback, equals more warming. This is positive feedback. A warmer climate equals more evaporation, equals more cloud cover, equals more reflection of solar radiation, equals cooling. This is negative feedback. So, addition of water vapor may contribute both positive and negative feedbacks to warming. It is unlikely that we will be able to substantially reduce anthropogenic greenhouse gas emissions in the near future. Models predict that industrialization and resource use associated with rapid economic growth will have a more significant impact on global warming than population growth. The results of global mean temperature change models for 3 scenarios, 1900 to the year 2100. Each plot corresponds to a different greenhouse gas emissions scenario. Scenario A2 assumes slow economic growth, rapid population growth, and slow technological changes favoring the preservation of fossil fuels as the dominant energy source. Scenario A1B presumes a rapid economic growth, moderate population growth, and a balance between old and new energy sources. Scenario B1 involves moderate economic and population growth with emphasis on new technologies available to all nations. Scientists use sophisticated computer models that use millions of calculations to try to simulate climate factors over the entire Earth system. Modern models seek to represent all key factors, including incoming solar radiation, outgoing radiation, wind speed and direction, cloud types, precipitation types and amounts, changes in dimensions of ice sheets, vegetation types, atmospheric gas concentrations, temperature stratification of the ocean, and continental topography. Climate model configurations. The climate models divide Earth's surface into a grid, with each square representing the base of an atmospheric column divided into a series of levels. The models calculate natural phenomena such as wind patterns, heat transfer, solar radiation, and moisture content for each grid square. B. Climate models characterize the conditions in each square of the grid and then set the model in motion to simulate how the climate evolves. The modeling results. All models tend to generate the same major trends that are observed in actual climate data. Multiple models produce similar results. The results depend on the complexity of the model, for example, the grid size, the number of levels, and the time step. Predicted temperature changes are averages, and they mask the fact that temperatures could increase more than 18 degrees Fahrenheit in some places and fall in other places. Example, warming causes the melting of Greenland ice, contributes fresh water to the ocean, affecting the Gulf Stream and cooling Europe. Most models predict greater temperature increases in northern latitudes and potential cooling in parts of the Southern Hemisphere. See, global climate change is not just about global warming. The projected annual mean surface warming for the scenarios B1 and A1 and A2 for the time periods 2046 to 2065 and 2080 to 2099. The temperature changes are relative to the average of the period 1980 to 1999. A warming effect is least for the sections of the Southern Ocean and the Northern Atlantic Ocean, and greatest for the northernmost latitudes. The predicted temperature increases for the United States are between 2 and 6 degrees Celsius, or 4 and 11 degrees Fahrenheit, except for Alaska, where the temperatures may increase by as much as 18 degrees Fahrenheit or more. Think about this. What would you do if temperatures here increase by an average of 10 degrees Fahrenheit? Most recent research indicates that changes will be most extreme in the developing nations who may not have the resources to deal with them. The wealthy nations, who produce most of the greenhouse gases, will be the least affected and more able to deal with the changes. We can crank up our AC. Can everybody else? The model changes to precipitation comparing 2090 to 2099 to 1980 to 1999. The evaporation and precipitation will increase due to warming, but extra rainfall would not be distributed evenly around the globe. It'll be higher in equatorial regions and for the oceans versus the continents. Global warming is very complex. Should we do anything? Can we do anything? Some countries might benefit from the warming. Earth was much hotter in the past, during the Mesozoic era. In 1992, nations pledged to reduce emissions by the year 2000. It didn't happen. In 1997, the Kyoto Protocol represents an agreement among developed nations to reduce greenhouse emissions to the 1990 levels by the years 2008 to 2012, and 6 to 8% lower in following years. In December of 2015, efforts to minimize future global warming took a big step forward when the world's nations negotiated the Paris Agreement, which seeks to hold the increase in global average temperatures to less than 2 degrees Celsius above pre-industrial levels. Countries are now more seriously considering options for reducing global warming emissions. Stay tuned. We can take direct action. Options to slow the buildup of greenhouse gases include, but are not limited to, conservation, replacing high carbon fuels, new transportation fuels, and forest management. Possible carbon emissions through the mid-century. If emissions do not increase, they would follow the flat path. However, at current trends, it is more likely that we will follow the emissions doubling path. The difference in carbon emissions for these two scenarios is represented by the stabilization triangle. Carbon sequestration. An active area of research for sequestering carbon dioxide involves injecting it into oil and gas reservoirs, deep salt formations, or abandoned mines. The expansion of carbon-free energy sources such as nuclear power and wind energy could account for 2 or more stabilization wedges of future carbon emissions. Problems? How do we get the mirrors up there? How do they stay up there? It assumes that we can trap carbon produced by human activity. What if there's a catastrophic release of this trapped gas? Altering one part of the Earth system to remedy human-induced changes on another could prove tricky or not useful at all. This concludes Chapter 17's lecture. I hope you have enjoyed this course.